Okay, good afternoon. This is the first class of the course titled Nanoscale Sensing Element and Device Production. I am Gianluca Piccinini, and together with my colleagues, Professor Danilo De Marchi, Maria Grazia Graziano, and Massimo Ruoroc, we prepared this course, and I hope that the classes will be interesting for you. So, now we can briefly consider the course organization and course content. So the course is formed by three parts. Part one is titled Modeling Molecules for Electronics. This first part will contain some classes. The first one is on Introduction to the course. The second one is on molecular electron extractor and modeling of molecules for nanoelectronic. The other one is on conduction mechanism in molecules. And the lab one, that will end the first part, is on Introduction to molecular simulation with a Gaussian simulator. So this first part obviously is devoted to review some basic aspect of molecules, and the focus is on the electronic properties of molecules and how we can evaluate electronic properties starting from the chemical structure of molecules. The second part is molecule and devices. In this part, some classes will be focused on the chemical of molecules that had been used and are under investigation for nanoelectronics. So two lectures will be devoted to these topics. A second laboratory will be on electronic structure and molecular orbitals of molecules. Again, will be used Gaussian simulator. And some classes in the second part will be on molecular devices, wires, diodes, switches, transistor, memories, and molecular QCA. This part will finish with IVU simulation, current simulation of molecular devices with virtual nanolab. The last part, the third one of the course, will be on technology and system. In this last part, we will study, we will consider how we can interface molecular device with CMOS structures. So during this part, we understand how the signal produced by molecular device will be measured and revealed by this kind of electronic structure. So a readout architecture for molecular system will be studied and described. Also measurement and characterization technique for molecular system will be introduced. The last lab, and this lab will end the course, will be on process fabrication for nanoelectron, nanogaps structure. Okay, so if you have any question, I can answer you. Otherwise, we can continue on the introduction. So, why molecular electronics? And probably we have to understand advantages of molecular structures. For all of you, is well known this kind of diagram where you can see how here by here the channel length is reduced by scaling, and the number of devices per integrated circuit will grow up. So what is interesting to note is that at 2020, the channel length of MOS transistor will be less than 10 nanometers. So this kind of rate is well described by the Moore law that will inform us that approximately every 3 years the channel length will be reduced by 30%. In other words, we can say that the channel length halves every 6 years. So we can understand that this trend cannot furtherly supported by current technology, because when we have so short devices, many problems arise from the technological point of view, and probably will be very hard to find a solution in the traditional technologies. This is a typical structure for a submicron. This transistor has a channel length of approximately 50 nanometers. So probably you can recognize in this structure the gate structure that is probably is polysilicon with silicide on the top. But what you can notice is that the structure is quite complex because we have to introduce many advanced techniques to overcome short channel problems. In particular, you know that the gate structure is a very complex structure where you have many layers with many interfaces. So we can do some additional consideration on dimension of CMOS transistor and on the interfaces. So now I can try with you to do some simple estimation. So when you have a MOS transistor like that, the structure is typically done in this way. So we have the silicon substrate. Generally is ultra thin body technology, but it doesn't matter, but this is silicon. On this silicon we have realized the two structures, source and drain diffusion. And here we have the gate structure. The gate structure, if we can note on the previous slide, you can see the spacer on the both sides of the gate structure. So here we have a spacer. Inside spacer we have oxide. Oxide or dielectric. Dielectric is a very critical part of the device. Traditionally, that structure is silicon oxide, but you know that now this is a stack of materials because you have silicon over a thin layer, one or two atomic planes of buffer of silicon oxide. Over that, we have the high K dielectric, generally today hafnium dioxide. So, and below, and here we have generally the gate, could be if traditionals here can be polysilicon, and below silicide. So we can count the interfaces. The number of interfaces in this stack is 1, 2, 3, and each of one can be a problem, as we will see. But now we can do another kind of consideration. If you remember a well-known equation, very simple equation, to estimate the threshold voltage of this transistor, Vt is equal to flat band voltage plus 2 Vp plus square root root of 2Q 2 phi p over oxide capacitance. Now we can do some remarks. Flat band voltage and phi p depend mainly on the doping level and on the working function of the different material in the system. So now we can let's stay there. But this term can be seen is equivalent minus depletion charge, the term under the square root, over oxide capacitance. In other words, this quantity is associated with the depleted region below the gate oxide. So the threshold voltage depends mainly on the quantity of ions that you have there. So this is a P substrate. So here we have negative ions. The quantity of this charge influence mainly the value of threshold voltage. So now we can do very simple calculation. So you know that this equation is without a dimension, so you can estimate threshold voltage without knowing the real dimension, the actual dimension of the transistor. But you know also that the main short channel equation can be derived by considering the total quantity of charge, so we can multiply these two terms for the area of the gate. The area of the gate is length L and width in that direction W. So it's clear that in a large transistor these two terms are useless for the estimation of Vt. But when the dimensions are getting smaller, this quantity should be corrected by many factors. But we can do the same here. This is a density of charge. This is a density of capacitance. But if we multiply Qd in this way, this will be a charge, and this will be a capacitance. So we can try to evaluate the total charge in the channel that will define the threshold voltage. So as I said, the transistor is 30 nanometers channel length. So we can say L, we can write here, should be approximately 30 nanometers. We can imagine that W should be 50 nanometers. The depletion layer depth, generally with a doping level that we can estimate about 10 to 18 per cubic centimeters, this depth could be 10 nanometers approximately. So now we can try to estimate the quantity of charge in that layer. So I can try to multiply W, sorry? Just a second, please. No, cosa? Verde. Non usare il verde. I know, but ok. Da dove riprendo? Where I can start from this calculation. So, okay. Now we can evaluate the volume of this area. Now I can redraw the interested area. The volume will be this one, the depleted layer below oxide. So, the volume will be W. Now I can erase this 1, so it's not... okay. The volume will be L dot W dot XD, depletion depth. So we can substitute numbers, and what we discover is L is 30 nanometers, in other words, in centimeter. W will be 5 dot centimeter, and the depth will be 1 over. So this value will be in cubic centimeters. So we can do this simple, and we discover will be 15 . All right. So now we can try to evaluate the quantity of charge there. The quantity of charge is related to the number of ions, but the number of ions depend on the doping level. Doping level, as we said, is just 10 to 12. So what we have is that in that region, probably we have just 15 atoms of doping. The dopant that will define the threshold voltage of this transistor will be just 15. So number of doping atoms will be 15. In other words, process variation will be relevant in terms of threshold voltage, because if we are not able to control with enough precision the doping process, few atoms less or few atoms more can change the threshold voltage of many, many millivolts. So this is a very, very interesting effect of the scaled dimension. So in traditional process, this kind of problem must be solved, but it's very, very difficult. Second thing, you know, if you remember, that the threshold voltage, I can rewrite here, as the term minus QD over oxide capacitance. Oxide capacitance depend on the materials that the gate is done and on the thickness of the gate. Again, I can reconsider this structure, and we can say that the gate stack and the thickness of this dielectric can be few nanometers, 10 angstrom. And so it's very, very difficult, again, to control this thickness. And you can understand that both quantity, charge, and capacitance are, must be controlled with high precision to get the threshold voltage required by the process. The second thing that we can notice it, as I said, we have many interfaces. Many interfaces in crystal means many dangling bonds. So many charges can be trapped between different layers of the material. So charges trapped there means again new terms, new quantity that can influence the threshold voltage. So on this basis, we can understand that the scaling rules will meet a serious problem in the next future, because we understand that the process variation, quality of interfaces, probably will be not enough good to maintain a control on the threshold voltage required by electronic systems today. So, molecular electronics can be a good response, could be a good solution for this problem. Since when you produce molecules, molecules are the same, all the same, because the synthesis process generally will produce identical molecules. And this depends only on the quality of the synthesis, but is not required to control directly atoms like in traditional processes. Second point, second advantage for molecular electronics. Molecules have no dangling bonds. So that means that the interface that you can produce are without trapped charges. So this is another important advantage with respect to the traditional process. Third, molecules are tunable. In other words, you can define the function of the molecule, defining the internal structure of the molecules themselves. So you can define how the charges will be in the molecules, how the charges can be moved inside the molecules. Molecular electronics many times is described as a new frontier, because with molecular electronics you can use self-assembly techniques. Self-assembly techniques, again, can be a good solution to overcome limitation of traditional technological processes. Self-assembly means that you can produce devices without a direct control of the geometries. For instance, here we have just a part of a crossbar. Probably is a crossbar built up by nanowires, gold nanowires. So you have a cross between two gold nanowires, and you can define, you can realize a molecular device simply by that self-assembled monolayers of molecules that can be produced there. And so you know that only the cross-section between the horizontal X and Y direction wire, only in that place you will produce a electronic device without any other control. So if you will prepare a crossbar built up by gold nanowires, you can produce many electron devices, millions of electron devices, simply by exposing the gold nanowires to molecules able to assembly, to bound to gold. Self-assembly is a well-known technique, and we will consider many times during next classes also my colleagues will explain you many applications and many strategies to realize devices by means of self-assembly. The most used technique is sulfur gold bond, like this. In this case, we have two electrodes, gold electrode on the left, on the right, and a organic compound, probably that is a thiophene, is bound to the electrode by means of two sulfur atoms. Sulfur with gold will produce very strong bonds, and the quality of the stratus is very high, also in terms of conductivity. So this is a very used technique in molecular electronics to realize molecular devices. But application of molecular electronics are really wide because, as I said, electronic function can be defined, can be adjusted simply by designing a proper chemical structure. So we can define a very large set of functions simply defining the molecules and the internal structure. So we can define molecular wires. We will study very well why that kind of organic compound. You can discover that in that chain you have some benzene rings. So we discover quite early why that kind of molecules are good candidates and are good element for electron transport. But you can also produce diodes. Diodes, if you synthesize molecules like these, where we have an acceptor and donor part, each of one have a different behavior when you bias the molecules, and the interaction of electrons with molecular orbitals inside the structure will be modified by polarity of external bias, and so you have a rectifying effect like diodes. We can try to design molecular FET. In this scheme, you can recognize a structure not so different from the traditional MOSFET one, because you have two electrodes, source and drain, a third electron on the top that is the gate electrode. And by using the gate electron, you can, with the electric field, you can modify the energy level of the molecules, and so you can modify and control the electric conductivity of this structure. As you will discover, this idea is too bound to the past, because this is an idea that is obviously derived from the experience on a MOSFET transistor, but we will discover that this structure is not so good for molecular application, because the electric field required to influence molecules require oxide thickness so thin that it's very difficult to realize it. And with molecules, you can also define completely new devices. Like this, you have similar to a switch, but is a switch where charges are moved inside the molecules without transport of electrons outside. So this can be used to define a new set of application, new set of architectures, and some classes during this course will be devoted to the study of QCA based on molecular switches like this. So, to end this brief introduction, we can say that molecular electronics is a challenging research field because it's multidisciplinary. So, in other words, molecular electronics require many effort on electronics, on chemistry and biochemistry, on computational chemistry, and on process technology. So only with a good knowledge on all these research field, new devices and new architecture for electronic application can be defined. Ok, thank you. Top. Allora, seconda lezione.